This talk is mainly at a, I would say, very broad level. It's about a topic which we've only started recently thinking about, which is some really foundational issues about what happens when you put matter in a cavity, an optical cavity, which I assume in the prior lectures you all know what an optical cavity is. You've heard plenty about them in this series. Okay. And of course, people have studied this for many decades, 50 plus years, I guess, at some level. And there have been a lot of beautiful experiments with sort of cold atoms in cavities, also beautiful experiments with real materials in cavities now. They've seen that the cavities can affect the many-body properties. You'll even see a lot of things about new phases of matter being predicted by theorists. And basically what I want to claim is that we don't even know what it means to be a phase of a matter in a cavity. And I'll try to get you to the point where you understand that at the end. So this isn't going to be a talk where I regale you with a lot of results, because I only have a couple results in this field, and I'll mention them. But basically, what I want to do is convince you that there are actually deep conceptual issues that need addressed and point towards how we might begin addressing some of these issues. Okay, so hence the title. That was your last chance to scan the QR code. I'll put it up again at the end. What is a phase of matter for materials in cavities? And at the same time, I want to take the chance to introduce something I call Dicke materials, which mathematically are almost the same thing as atoms in a cavity or spins in a cavity, material in a cavity, but they're actually physically quite different. So instead of a real optical cavity, you have some other degree of freedom that plays the role of a cavity. And it's mathematically the same, so you can borrow all the ideas you have from understanding Dicke materials and apply them. And I should say this is super informal, so I'll probably use the board a bit. I was actually originally going to do all of this on the board, but then I decided to make some pictures. So I do hope you will just ask lots of questions and we can discuss things. This is really me grappling out loud with what I think are the big issues of this field, and I would love to brainstorm with you and try and work our way through some of this. So before I talk about any of the questions here, these are the people who have been working on this in my group mostly. Some others, actually Joseph has begun doing some work on this as well. But by and large, this idea of Dicke materials has been done by my postdoc Vaibhav Sharma in collaboration with several experimentalists and other theory faculty here. Some of the more deeper conceptual issues really originated out of mathematical physics work that was done with Jiwan Wang, a former student in the group. And then the detailed modeling of what are called orthoferrites, which are an example of these Dicke materials, was done by Sohail Dasgupta and Hao-Tien Wei. Hao-Tien's right there, and Sohail's now a postdoc in Birmingham. And Jonathan Stepp has been continuing this and trying to understand better some features. I will actually talk very little about them. To give you a sense of who I am, this is not the only thing I work on. I mostly spend my life thinking about cold atoms without cavities. And so we're very interested in fermions and lattices or engineered lattices, interested in how can we use internal states of these ultra-cold atoms to generate things that wouldn't otherwise be possible in nature, and how can we use quantum computers or quantum simulators or some hybrid of these two to solve computational problems. Yeah, please.
Perspective question.
Please.
I noticed you mentioned quantum strings.
Oh, yeah. Yeah, I'll talk about this the whole time, too. So this is a really simple idea. So it's just an interacting collection of matter that, say, can float around in 3 dimensions, but under the effect of its own interactions, it collapses down to a 1-dimensional object. So it's no different than your shoestring or a protein. These are both 1-dimensional objects that live in 3D. The difference is this is quantum. And actually, there's no direct experimental study of extended quantum objects like this. Lots of classical objects like this we study. And so that's something that we're very interested in, and our collaborators have actually seen dynamical versions of this in experiments with Rydberg atoms. But they are very simple strings, they're not relativistic strings, and there's a lot of very rich physics there. Yeah. Not fractons is actually, well, no, it's not. In other models, you get things that are similar to just the strings you get in topological spin liquids. Great questions. Come to my office sometime. I'll tell you more. I do want to focus on the cavity stuff because I think that's where the interest of most of the people here lie. Or if we have time, or if we just get really distracted, we can come back to it. So the three big sections of the talk and the three things I want you to remember from today. First is that this is just an exciting research frontier. Putting a real material in a cavity lets you shift its properties. We're really only at the beginning of engineering that. I'm not sure how far the engineering can be pushed, but for everyone I've talked to, it seems like there's no immediate fundamental limit to how much further we can push it. So we can clearly get a lot further than we are. And I think that will be very interesting to look at. The second main you can use this, you put things in a cavity, and this lets you control the materials properties. Maybe you can shift a transition temperature or induce a new phase. Something I'll say just a little bit about is you can actually engineer entanglement, create large-scale macroscopic entanglement, which is very hard to do. And there's an intrinsic robustness to it when you do it this way. And also to just engineer things that might be impossible. So there might be, for example, you might have a theorem, you might remember a theorem called the Merman-Wagner theorem that says if I have a continuous symmetry, it can't be broken in 2 dimensions. And so there's no 2-dimensional material that breaks a continuous symmetry. There are no phases of matter that break that continuous symmetry. Yet in a cavity, this totally fails. And so you can engineer phases of matter that just wouldn't be possible otherwise. Okay, the second idea I want you to take away is that you do have this analog between materials and cavities and these other systems, which we've coined Dickey materials, for lack of a better word, and I'll explain briefly how that works. And lastly, that there are these conceptual issues, which there's a long list of them, like a dozen related questions we could talk about, but I think they all kind of bottom out, and you really see how fundamental it is when we ask what is the definition of a phase of matter when we have a cavity. And so that's where I want to get to by the end of today. Okay, so here's just a snapshot of a few examples. Does anyone have a laser pointer? I guess I can use my pointer here. Here are a few examples of different materials that people have put in cavities. And in panel A, so the one that's being pointed at there, this is a 2-dimensional electron gas that I think it's, or is this graphene? Somebody knows. Elijah? This is a 2-deg. Yeah, I think so. Yeah, that's right. This is a 2-deg, that 2-dimensional electron gas that is placed in a strong external magnetic field. And as a result, you get a quantum Hall effect. This is a fancy topological phase of matter. This is something without a cavity, has been known for a long time. And you get resistance that's quantized at very specific values, multiples of E² over H, 2H. And this is essentially that's for the transverse resistance. The longitudinal resistance, which is what is being shown down here, dips to 0 in these quantum Hall states. A quantum Hall state is actually a resistor if you try to pass current through it from end to end. And so that is certainly something that has been observed many times and is very clean. But when you put these systems in a cavity, it actually destroys this. All of a sudden, the cavity allows the quantum Hall state to have a finite resistance. Sorry, it's a perfect conductor, not an insulator. Okay, anyways, it's something that 0 becomes non-zero. I don't want to get into quantum Hall physics today. As another example, this is in this panel C. People have taken a charge density wave material, tantalum disulfide or something along these lines, and this is something that at high temperature, it's just a metal, and as you decrease the temperature, the electrons form a density wave. And what happens in the cavity is it can actually shift that transition temperature. So in this plot, this is measuring, as a function of temperature, what's happening in these sort of hysteresis diagrams. And you see the red curve is the free space hysteresis diagram. The blue curve is the one in this, microwave cavity. And you see that it certainly shifts all of the temperatures of that physics. Not by a ton, by 10 degrees or something, but there's clearly an effect. And there are many other examples. They get more and more controversial. There are many controversial and disputed examples because it can be very difficult to rule out whether you change things by actually modifying the electromagnetic vacuum as a cavity does, or because you stuck a material in a cavity and something's happening on the surface, or the cavity is changing the thermal environment somehow. So you really have to worry about all of those things to make convincing claims. But I think these are two pretty solid examples. Okay. And so here we are. Oh, sorry. And then there are these predictions from theory, for example, that if you put graphene in a chiral cavity, so which has a chiral optical mode, that this will induce a topological band structure. It opens a gap in graphene and gives you a topological band structure. And there have been several predictions like this. Jun Kono has worked on such things here, and it's a very interesting area. And then going back to my main point, if they're claiming that this introduces a topological band structure, and the reason we care about topological band structures is because a topological band is different than a non-topological band. They're different phases of matter. What does this mean if we don't even know what a phase of matter is? What are we actually talking about? Okay. All right, so just to refresh you, have you talked about decay models in this lecture series at all? I'm not seeing it. Okay.
Went over it.
Cool. I'll review it. It's fine. So, I mean, and you don't need to actually look at any equations in this talk. There aren't going to be many. Mainly, the slides are just notes for me to remember what I wanted to talk about. So, we have this situation where we have a bunch of two-level systems. I may call them atoms, but they're just two-level systems that could be, disorder fluctuators in a solid. They could be spins. They could be two electronic levels of an atom. These are just floating around either in free space or in some inert material we don't care about. And now we put these inside two mirrors that form a cavity, selecting out a single mode of the electromagnetic field. Okay, so there are kind of two relevant degrees of freedom. One is the spin degree of freedom, the two-level systems, of which we usually think it's not just one or two, but there are many of them. I have 10 to the 12 or 10 to the 15 or 10 to the 18 different spins in this cavity. And then the other degree of freedom is this bosonic mode, which is the cavity degree of freedom. And if you care about the Hamiltonian, it's written down here. So we have a cavity mode with energy h bar omega cavity, and then that's just the number operator of the cavity mode. I have a spin degree of freedom where each spin has an energy for cost for flipping that is h bar times omega mat for material. And then there's some coupling G. And what does this coupling G do? It couples the A dagger plus A. If you remember how harmonic oscillators work, this is just like the X position of that oscillator. If it's a light mode, it's something like the electric field of that oscillator that couples to the spin. So in other words, the spin and the electric field want to align. This is just D dot E, dipole dot electric field. We all know that's the energy of a dipole in an electric field, right? So this term is how things are coupled. And maybe the easiest thing to think about here is to just pick out one of the terms. So sigma x is sigma plus plus sigma minus. And so there are terms where what I'm doing is I'm putting in a photon and I'm flipping a spin. Each one of the terms in this coupling term G is doing this. I can either put in a flip a spin and take out a photon, or I can flip a spin and put in a photon. Those are both allowed and important for the physics that you get. There's also this final term, which is just kind of the a squared term. It comes up when you write out the Hamiltonian. It is dependent on the coupling between the light and the matter. We're not going to pay too much attention to this term, but it is absolutely crucial and the source of several controversies in what may actually happen if you put materials in a cavity. Okay. For us, when we start dealing with decay materials, we'll be able to get rid of this term that causes all the controversies, and we'll have a much cleaner system to consider. Okay, so is the setup, the model clear? You don't need to remember the exact notation, but maybe remember that G is the coupling between the electromagnetic field and the spins. Okay. Happy, unhappy, bored? Oh, okay, I'm getting one thumb up. That's perfect. Okay, so this is a canonical model of quantum optics. In this case, this has been studied since, I guess, 1973 by Hepp and Lieb, and related things were studied by Dickey, hence the name back in the 1950s. It has interesting phase transitions. It has entanglement in the ground state. And in cold atoms, the dynamics of this have been studied, for example, by Tilman Esslinger in very interesting papers several years ago. Same model and just very diverse applications. Every quantum optician studies this model at some point. And so this superradiant phase transition is sketched here. This is a phase diagram that shows what happens as I change the ratio of the matter frequency to the cavity frequency on the vertical axis, and this coupling strength, G, on the horizontal axis. And if you like, just pick some value here. And let's just look at what happens to 0. Actually, sorry, this is not a phase diagram. This is the spectrum. I copied the wrong figure out of the paper. This is the spectrum, but there is a related phase diagram. So we can actually just think about the spectrum where it goes to 0. The frequency goes to 0 is indicating the phase transition. And indeed, that's shown in the shaded regions that I have a normal phase on the left and a superradiant phase on the right. And so what's actually happening here? So if there's no coupling between the spins and the cavities, the spins just kind of point in random directions. The cavity field just fluctuates on its own, and there's no locking between them. But as you turn up this coupling, there is no longer a symmetry where I can independently change the direction of the electric field or the sign of the electric field and the direction of the spins. They'll want to lock together. And so I think this is very intuitive, and you can get this as simply as just taking a mean field treatment of this Hamiltonian. If you just factor this A dagger plus A and this collective spin with mean field theory, you get exactly the right picture. And in fact, for this simple model, the mean field theory gives you the exact phase diagram. So this is an extremely simple model, if only all phases were so simple for us. Another key thing that is very different from normal materials is that if I have these atoms in a cavity, maybe here a picture would be useful. So if I have these atoms in a cavity, here's one, here's another. Then when I flip this spin, so it rotates from up to down, let's say, I emit some photon, think of it as a wave packet for better or worse, and this photon will start propagating over here. Now, as the photon passes by this, it can flip the spin of this guy. That actually doesn't require a cavity. That's how interactions work in free space as well. But what happens in the cavity is it keeps this photon in the cavity. And so now this wave packet goes back and forth and back and forth millions of times, because the speed of light is fast, remember. So it goes back and forth millions of times before a single spin can really do much dynamics on its own. And as a result, this spin talks to every other spin in the cavity. And the interaction here, it's not local in the sense of nearest neighbor. It's not local in the sense even of a Coulomb law where it decays like 1 over r. Everything talks to everything. And this is really important for what makes these systems different compared to what we're used to thinking about in condensed matter. And I'll tell you what makes it different from the usual quantum optics scenarios a little bit later as well. Okay, the final thing, which I think in the interest of time I'm not going to say too much about, is that when you actually go look at this ground state, mean field theory does great for predicting the phase diagram, but you can ask for more information than the phase diagram. And for example, you can ask, what is the entanglement in the ground state? And remarkably, there's a sort of special kind of entanglement right at the phase transition known as perfect two-mode squeezing. This is something collaborators of ours discovered a few years ago, and Motoaki Bamba especially. And this perfect two-mode squeezing might be interesting for, I don't know, quantum sensing or something like that, but I don't want to go down that road because I think it's very complicated in this setting. I just think it's purely fascinating that you can have this concept of entanglement and really see it survive potentially in a real material. This is not at all an easy conclusion. Certainly our models of most materials, if you go do the theory, they predict that it's entangled. But in fact, seeing that that entanglement survives or measuring it in an experiment is extremely difficult because very tiny perturbations can kill that entanglement. And so this is a chance with some good reasons to believe that the entanglement could be robust, and it's an interesting place to look for entanglement. Regardless, it gives you a whole paradigm of harnessing all the things the quantum opticians have studied that tell you have entanglement in the Dickey model and applying it to real materials now. Okay, so it gives you a control knob for generating entanglement.
Quick question. So when you think about entanglement, right, in this setting, is it entanglement between the photons and the spin or between spins?
Really good question. It's both. So it turns out if you look at the spins, they're entangled with each other, and there's an entanglement between the bosonic mode and the spins. The perfect squeezing is sort of between the two. And so that's a very sort of strong form of entanglement. But there is also strong entanglement, not perfect squeezing, but still a lot of squeezing for the spins.
I've noticed you dropped the D-term.
Yes. Yeah, it affects everything miserably. So had I included the D term, there would be no phase transition. Everything's always the normal phase. And that's one reason we're going to like these Dickey materials that let us drop the D term. Yeah, so for infinitesimal D, I should go recall the literature. I don't think it's actually totally settled because there are also other terms I'm dropping, like dipole-dipole interaction terms that you have to include consistently to treat electromagnetic problems.
Why there is a D term.
Okay, I'll come back to your first question, but let's see where the D term is. So if I write the Hamiltonian for particles in a electric field, it's the A squared term. So this is basically saying you take the A of the cavity evaluated at where each atom sits, and that gives you the A squared term. So it is a light matter coupling, even though it's a purely A squared term, because it's really sum over positions J, A of R, J, where these are the positions squared, times some constants. Okay, so that's where it comes from. Now, I'm not actually sure. I think what happens is for infinitesimal D, it comes down from infinity. But if you're actually doing electromagnetism, what you see is that the strength of these terms are not arbitrary. So where do all these terms come from? So I have a P squared over 2m minus A dot P. We'll ignore commutation. It doesn't really matter. Over m plus A squared over 2m and some appropriate unit choice. So there's this A squared term. And then the D dot E term, this sigma dot A plus A dagger term is really this term. You can sort of integrate by parts or do gauge transform to rewrite this as D dot E with minus sign. And so the coefficient in this term and this term are actually not independent. They're constrained by gauge invariance. And so you don't have that freedom. But in a Dickey material, because it's not a real light mode, there should still be a D term because there's nothing that forbids it, so anything that's allowed by symmetry must be there. But it can be very small, and therefore we should have something that looks close to this. So if you go all the way to the electromagnetic case, I think there's a consensus it goes out to infinity, but as you perturb away from that, it probably smoothly goes between the two limits. Okay. All right, let me just skip that next slide and just say that, real materials are not Dickey models. So I'm going to be using this as a framework to think about what happens for real materials in cavities. But real materials are complicated. And just to remind you of this is a typical solid state lattice structure. It's a pyrochlore. Who knows? It's got very interesting physics. It's not just a bunch of non-interacting spins. And that's something we're going to have to contend with. They have their own life. And so don't forget about that. We won't forget about that. That's one of the big questions. So hopefully this gives you just some review, some background, and gets the idea that this is an exciting field across. So now what I want to tell you about is these Dickey materials as a spin on the idea of cavity-coupled materials. And I think it's a very beautiful idea. So what we want to do is we want to boil down what agrees with enough of the ingredients of a Dickey model that it's going to still have some remnants of the same physics. And of course, what ingredients you want Depends on what remnants and what physics you want to have remnants of. But I'll try to give you some idea here. So what we're looking for is certainly a bunch of spins, and we want those spins to couple to a bosonic mode. And there are lots and lots of systems in nature that do this in one fashion or another. So one picture on the left here comes from trapped ion quantum simulators. Guido's group and all the people here from it are experts on this. Here you have charged ions in some linear arrangement or maybe a two-dimensional arrangement. They form a crystal, and crystals vibrate. Vibrations of crystals, the phonons, are bosonic modes. And so if you have a spin on these atoms, it can couple to those bosonic modes if you engineer it correctly. And this sounds a lot like we've said about Dicke models, and I'll say more in a second about how and when this works. Another example is I take, hemoglobin or some protein. This has a bunch of spins, a bunch of nuclear spins hanging around on hydrogen, and it vibrates. So we have spins, we have bosons, we have some of the ingredients here. And particularly pertinent to what we've been doing with Jun and Hanyu and others are multi-component magnets. So you'd have some atoms in a material that act as the atoms and some that act as the bosons. But let's think about what we actually want to make this kind of work out. So if we want to have the analog of a cavity, we don't just want to have bosonic modes. We want to have one relevant bosonic mode, right? It's a single mode cavity, and we don't want all the complications coming from the other modes. And so, if I take hemoglobin, it presumably has a lot of bosonic modes. That's not going to be a very good molecule to use. But we might be able to find a nice molecule, work at low enough temperatures that only one mode of that molecule couples to our spins. So this might be a way we could get the quote cavity. I want it to be a quote optical cavity, or having to do with light, which means precisely this, that I want this mode to move around very quickly. I want to make sure that if I flip a spin in my molecule, that those phonons, if that's what I was doing, go back and forth a lot of times over the whole system to couple it to everything. If I don't have that separation of energy scales between the dynamics of the individual spins and the velocity of that bosonic mode, it's not going to look like a Dicke model. You will effectively see the range of the interactions coming from the finite speed of propagation. And the other thing is, in the Dicke model, all of those atoms didn't talk to each other directly. They could only talk to each other by exciting the cavity. And so if we want some remnant of that physics, then we also want to make sure those interactions aren't too strong. And then finally, you can imagine other terms. You could add disorder to the system. You could add coupling to phonons, like not the phonons you want, but other bad phonons or other degrees of freedom. And if you have those terms and they start to dominate the physics, maybe it's now so far from a Dicke model, you don't want to call it a Dicke material. So just to summarize, single mode, really fast dispersing bosonic mode, and independent spins other than the coupling through the bosonic mode. Those are kind of the three key ingredients. And the one that really gives the novelty that I'm most interested in, that causes the complications, the conceptual issues, is this optical requirement, that the mode velocity is very large. Because it's precisely this that tells me I can't think about short-range interactions anymore. So maybe if you relax the other assumptions, it's not a Dicke material anymore, but it would still have all the issues that I'm trying to indoctrinate you into caring about today. Okay, so let me give you a toy example rather than just talking abstractly. So this is not quite a real material, but this is a theorist version of a real material. So what I'm doing is I'm just taking two lines of spins. I have a top line of spin 1/2, and I have a bottom line of spin 1/2. And I'm coupling them in the following way. So the top line are just all coupled by some, say, Heisenberg coupling, some S.S coupling between the spins that is of strength J. The top row is connected to the bottom row by some coupling G, and then the bottom row doesn't talk amongst itself. And just conceptually, if you think about this, you can go do the math and show this. This actually maps on exactly to a Dicke model as long as G isn't too large. And the reason is that the top row creates a magnon mode. If I think about what are the excitations of this magnet, they're just spin waves where the spin, let's assume this was a ferromagnet, so all the spins went to a line, the low energy excitations are just wiggling of that. And so that acts as a bosonic mode, and that's my cavity.
What do you mean by G isn't too large? G is not exceeding omega?
G is much less than J for now. Yeah. To what extent this still counts as a Dickey model when they're comparable, which is maybe where you want to go for the interesting physics, is a more subtle thing. But in fact, you can make it work there if you're careful about band structures and things. Yeah. I mean, yeah, anyway, I'd be happy to talk more about that. So, and then clearly the bottom row is just independent. Everything works out kind of like we wanted. So how do we get this in a real material? Where should I look for Dickey materials? Well, any ideas? I think a lot of you know a lot more about materials than I do. I'm going to tell you one answer, but this is actually one of the big questions I have. Where should we look to find more Dickey materials other than the one we have? Anyone know a system that looks like this? It's a genuine question. Like I'm desperate. Well, let me know if you come up with one or stumble on one. I think these will have very interesting properties that they inherit from the Dickey model. So what do we need? Here's a more realistic looking condensed matter type model. I still have my top row, my bottom row. I have all the couplings before, but now I allow the spins on the bottom to be coupled, right? They're not going to be uncoupled. Of course, real materials might be higher dimension. They might be complex lattice structures. They might have spin anisotropies. So I'm still only capturing some of this in the cartoon, but I hope you get the idea.
May I ask, what is the very complex playing the role of the photon energy in this simplified model?
Yeah, it's the J.
But isn't the leptons gapless?
They are, yeah.
So how can this give you a finite?
So, I mean, think about putting it in, this is a finite system, so there's some finite, it's a finite size gap in that. Well, I don't think necessarily. I know why you're saying it, okay. In literally the setup I just said, it has to be a small system, perhaps. I mean, yeah, talk to me afterwards. I think we can say more about this. Yeah, I can tell you about the mapping. Okay, so what do we need? We need some sort of ratio where this JBB is much less than the JAA. J bottom bottom is less than J top top. Okay, that's actually maybe not too terrible to do, but I also want the JAB to be big. I don't want it to be negligible, at least, because then there'd be no coupling between my bosons and spins. So this gives you a pretty sort of interesting set of criteria that aren't so easy to satisfy. And I'm going to give you sort of the backwards version. I don't know, I think this material was stumbled on, and then we started to realize, somebody else started realizing it was Dickey stuff. But I'm going to try and rationalize how could we have predicted this material. So if I want to make sure that the spin-spin couplings JBB are really small, then I could use something like rare earth atoms. Rare earth atoms, the spins are in the F shell, and so those are pretty tightly bound, and there's very little coupling between the atoms because they're too far away to have much spin coupling. Okay, and for the A, the top row, maybe I would use something like iron, which has a very strong coupling. It has nice electrons that want to delocalize, and so I can get large spin-spin interactions. So that at least would give me that JAA was much less than JBB. This is going to look something like a Dickey model. And then I guess you just have to search for combinations of rare earth atoms and other, say, d-electron atoms that have a good coupling that also give you a large JAB, that give you a good coupling between the top and bottom row. And I don't know any simple criterion for thinking about that. But we know an answer. Oh, no. Well, I hid the answer with that. Okay, you can imagine what's underneath it, right? I don't know. Repeat this. Just repeat the octahedra down here. So this is an erbium orthoferrite. These are our best candidate for a Dickey material at the moment, at least that I know of. I haven't actually searched that extensively. It just happened to have stumbled on it. But this is a case where you have nice kind of factor of 10 separations between the JAA, the JAB, and the JBB. Now, the sad thing is that this is quite complicated, and the couplings between the erbium, which is this sort of thing, and the iron are very spin anisotropic. Like, they're just complicated. You have Jalazinski-Maria terms, if that means anything to you. They have spin anisotropies. And so it's an ugly Hamiltonian, which I wouldn't dream of putting on the slide. It's got 14 terms or something, but it's the same general structure, that there's a bunch of spins that interact strongly with themselves, a bunch of spins that don't, and then a strong coupling between them. So now experiments have probed this. So in Jun's group, they've observed the sort of collective coupling between the two different modes, the spin and boson degree of freedom, where this boson is this magnon of the iron that it couples to. And recently, they have, in a collaboration done with us and Han Yuju's group, they've observed, using terahertz spectroscopy, the actual superradiant phase transition. So you go and you see that, just as predicted, some frequency goes to 0. That indicates the phase boundary, and it seems to agree with all the theory we have for mapping this to a Dickey model. So now there's a playground, a Dickey material, to explore this kind of physics in. And there's a playground, since we have these predictions from quantum optics that this system should be entangled. We have predictions from quantum optics about the squeezing. We have all this stuff. We can now start applying those ideas and trying to detect them using the tools of solid-state physics. And so that's a major goal of a collaboration that we have at the moment. Okay. Yeah.
So say I don't know anything about decay physics.
Yeah.
I'm a material scientist.
Yep.
I measure things on this material, I have some data.
Yeah.
Now, the decay way is a way to interpret the data.
Yeah.
But as a conventional solid-state physicist, I could also interpret it differently.
You could.
So,
And you would find this extremely boring if you interpret it as a conventional solid-state physicist. So this is basically saying mean field works great for the phase diagram, and it's a simple sort of spin, spins just flip around at the phase transition. That technically they can't. So the spins point in complicated directions here, which I don't even think I put on here, but they're all pointing in these complicated directions. And at the phase transition, they pick up a Y component, something like that. So this looks like super boring. Okay, so why do you care about this super boring physics? And I should say this was done. You can go read papers from, Moscow Journal of Physics, 1965, that have all done spectroscopy on this and modeled it in this very conventional way. So the real new thing here, so there are nice new experimental measurements and everything, but conceptually what's new here is that now when you go beyond just saying what is the phase diagram, and you start talking about observables, you talk about the spin-spin correlations. You talk about the spectroscopic response as a function of omega. Those are things that are actually extremely non-trivial, despite the fact that it's kind of a well-understood problem. They're not non-trivial to calculate. Okay, they are non-trivial physically, in that they have this large, robust squeezing. You can calculate them, although maybe less trivially than doing mean field theory. And so it's really the physical insights that they're giving you into the structure of correlations and things, which is not something which you would generically expect. So the type of thing you get is this two-mode squeezing, which is saying somehow the number of magnons and the number of the spin flips are locked together in some fashion. And that's just something that I don't think would be at all obvious from any ordinary condensed matter approach I know. I mean, you can definitely go back and understand it however you want, but I guess it's just stealing all these things that people have studied for decades in quantum optics and now revisiting those.
Right, so it's telling us that there is some operator, which is a mixture of the two type of magnons, which will support this large squeezing.
For example,
which you would not anticipate. But then it's, I guess, another challenge to actually measure.
That's I'm not going to touch that issue. That is a very interesting fundamental question of a very different sort, and it's exactly what Jun and Hanyu and our group are thinking about how to do. Terahertz sort of pump probe, or terahertz spectroscopy is how we're thinking about doing this, but of a very special kind. So.
That question is also why this paper ended up in Science Advances and not Science.
Yeah.
We had a reviewer that was like, well, Russian people saw this back in Russian times.
Russian times.
there was this phase transition, and they understood it magnetically. We don't need this light matter interaction model to be applied to this to understand what's happening.
Yeah.
Yeah. Fascinating.
So going back, I assume I think you're familiar with quantum Fisher information and these kind of ideas, and so you can actually consider this as as getting at the same sort of questions that this gives you. It's telling you that there's a non-trivial quantum Fisher information for some observable that can be detected with a static measurement, with a DC measurement. You don't have to do funny frequency integrations. But also, I really think it's just telling you that the physics is very different than you might think of. Actually, there's a further weirdness. So let me actually go back to the mean field idea. And the point is that mean field theory really should work on this material. And I don't know, this, of course, if you just go do it and fit it, okay, things will kind of work. But what I mean is if somehow you could do precision measurements and really everything, the mean field theory is actually the right universality class, which is maybe not what you'd expect for the finite temperature phase transition of a magnet in 3D. And it's a 3D material. No, not at finite temperature. The quantum phase transition would be mean field-like, but the finite temperature phase transition is still three-dimensional, which is below the upper critical dimension, right? So that might look a little mysterious, and it's precisely because of this separation of energy scales. So actually, if you turn on the perturbation, if you include the erbium-erbium couplings, that will now move you away from that mean field universality class. But because they're fine-tuned by a factor of 10 or 100 small compared to the other scales, it actually looks surprisingly in the, quote, wrong universality class over a long range of length scales. So that's a theory of predictions. Nobody's detected that. But it is something where it comes back down to this kind of idea that where this is coming from is now every one of those spins is averaging over a ton of its neighbors, and so it looks more mean field-like. Okay, but more mean field-like, well, it means simple for calculations and simple for universality classes does not necessarily mean low entanglement or uninteresting sort of experimental things. Okay, that's one of the most important points. I wanted to spend a lot of time, but that's actually the end of my second part, and I wanted to get into what the big conceptual issues actually are. Let me pause. Any other questions so far?
Yeah, so I'm touching on the material. So two questions. One is that is this material more icy-like or heavy? So whether the icy interaction more dominant or it's SU2 symmetric.
It's definitely not SU2 symmetric. And now I'm trying to think easy plane versus easy axis. Help me out, guys. It's
in X, Y. When you say easy plane, it's like you can fluctuate more freely than easy plane.
No, I mean, but these materials have strong DM couplings and things, so I'm not sure I want to call this,
Well, because if it's SU2 symmetric, then you the LSM0.
It's not SU2 symmetric. There's no obvious LSM constraint here. It's not SU2 symmetric because of the the Jałodziejski-Maria couplings, and there are also explicit spin anisotropies on all of the spins here. So it's just complicated. I'm trying to. I don't actually know what the symmetries of the model are, but they're discrete, I assume. There's no U1 symmetry left after all of this is there.
I mean, the iron is typically like a canted interferomagnet. So
Yeah.
Well, if the icy coupling is more dominant, then it makes sense that the magnet is gapped. Otherwise, it's gapped.
Yeah. So okay. So for the iron, it's certainly gapless, but the erbium couplings are really complicated.
Yeah. Another question is, so you say that the mean field theory works pretty well. Does this mean this material has a very strong long range interactions?
Effectively. So it's effectively that the erbiums have a strong long-range interaction that's mediated by the iron. The iron is like traveling at the, quote, speed of light in this cavity. And so every one of those, you just have to ask how, if it was light, you'd travel so far that you'd interact with a mole of other particles. When it's iron, it travels so far during the intrinsic dynamics that it interacts with maybe a radius of 10 sites or 100 sites. But actually, if you think about a radius of 10 sites, that's like 1,000 different spins you're averaging over, or 4 pi third times r cubed, so even more. Yeah. All right, so let me just try to give you a taste of, I think, what the conceptual issues are here. When does the class end? Is it 1? Is it, okay.
You got 13 minutes.
Oh, cool. You can just walk out whenever you've had enough. But so this field is marrying these ideas of condensed matter. These are real materials. You can hold them in your hand. They are marrying these with ideas from quantum optics, where we have these cavities that can control the bosonic modes in a very nice way and isolate them, and bringing ideas as well from entanglement, which was traditionally in quantum optics, into condensed matter. Of course, other people from other perspectives are also bringing these ideas into the field now. So it's a very, very interesting mix of stuff. But the issue is that these materials are fundamentally different than either what we study in quantum optics or condensed matter. And the culprit is the fact that we have both this long-range interaction and this short-range interaction. The super exchange, the Coulomb interaction, which I'm calling short-range because compared to this cavity, it's short-range. And also notice I'm just using cavities and decay materials interchangeably. It's the same idea for both. So one thing I'm going to try and remind you is that the framework for condensed matter relies on some notion of short-range interactions. If you don't have this, basically everything you know goes out the window, and I will try to convince you that this includes even any reasonable definition of phase of matter that you might have had. And the framework for quantum optics, it's tough to give such a unifying framework, but I'd say in these types of problems, in quantum optics, the trick you use to get insight is to use permutation invariance. So you have a bunch of spins in the cavity, but because none of them talk to each other, they only talk to the cavity, and you're pretending this cavity mode is uniform, you can swap positions of any pair of the atoms, and it doesn't change the answer. That's a symmetry. That's the permutation symmetry. And so this is just hugely simplifying, lets you do a lot of things you can't do elsewise. So, that might be your starting point. You might try to perturb in it. That's the sort of quantum optics way of doing it. But if I have both strong short-range interactions and strong long-range interactions, I'm out of luck, because I can't rely on either of these paradigms on their own, and I have to come up with a new way of doing that. And that's really where the research in my group at the moment is pointed. And I'm just going to give you, so unfortunately there's a whole stack of things we have to build up to get to the point where we can start making reasonable definitions of phases and proving the kinds of things we would like to. But I'll tell you what the sort of, what's lying at the ground floor that we're working on right now. Yeah, maybe just this comment. Permutation symmetry, how does it simplify the problem? It takes a 2 to the n dimensional Hilbert space and reduces it to some polynomially sized Hilbert space. And that's just because, let's just do a simple example. Here, imagine I had one spin flip. I could put that spin flip anywhere. Right? So here it's on the second side, here it's on the first, I can put it on the third, fifth, whatever. So just that sector, without using any symmetries, there are impossible states for where I could put that spin. But if I'm permutation symmetric, all I can get is something that's a equal superposition of all of these. Right? And this becomes, so I went from n states to 1. And when you start applying this to the whole 2 to the n dimensional space, each of these sectors breaks into some nice size space that you can deal with numerically or otherwise. The other thing you can do is do collective spin approximations. So you can, if you see everything that appears in your Hamiltonian for many permutational symmetric problems can be written as a sum over I of S sub I. And so we can define this to be a collective spin operator. And on its own, this doesn't get you very far until you go calculate the commutators of this big S, and you see it actually looks like a big spin. So if you have n spin 1/2, it's like having a spin n half. And as a result, this reduces just to a one particle problem. And so you just solve the one spin problem or two spin problem if you have two coupled types of spins. Okay, so that's sort of how you use permutation symmetry. Man, I don't know what happened to the builds here. That's fine, I'll tell you what's behind the builds. So this is how I want to tell you how locality is used in condensed matter physics. So even going before anything fancy, when you took statistical mechanics, you learned that one of the usually valid principles of matter, some people call it even the fourth law of thermodynamics, so I don't like this a ton, is that energy scales extensively with the system. Other properties also scale extensively with the system. The entropy scales extensively with the system. This is because you have finite range interactions. The surface it contributes an amount of energy proportional to the surface area, which for a big system is always much less than the volume, and so it's just negligible. So everything scales with the volume. Once you have this sort of cavity interaction, that's out the window. Things don't scale the right way anymore. More deeply and in ways that I'm not really going to get into, but hopefully you've seen some of these in your statistical mechanics or condensed matter class. Something we see a lot of in colloquia and in seminars these days are topological band structures. And there's this famous classification, the periodic table of topological band structures, which relies, it says here are 8 categories for this dimension and this set of symmetries. What are the possible types of topological band structures you could get? And that everything about proving that relies on locality. If you didn't have short range tunnelings in that case, this would not work. There's a version of this for interacting systems. There's a classification of what are called symmetry protected topological phases. So these are, again, interesting, huge variety of phases of matter that we now have a pretty good handle on. There's a classification in terms of what are called the cohomology groups. And that whole classification relies on locality. Essentially, well, anyways, I can tell you how that works. Maybe a more sort of familiar one or more elementary one is the Merman-Wagner theorem. So the Merman-Wagner theorem tells you that if you have a continuous symmetry that's broken, that this can't happen at finite temperature in 1D or 2D. Only in higher dimensions can you break this continuous symmetry. And the reason is essentially just because with the continuous symmetry, you can bend things around pretty easily. It doesn't take much energy to cause your continuous degrees of freedom to flop around. And so if this is flopping and this is flopping, they get uncorrelated at large distances unless they have enough neighbors to lock them into place. Okay, Merman-Wagner fails spectacularly, and even in one dimension with a cavity, if I have a cavity plus, say, a one-dimensional spin chain, I can get finite temperature long-range order, in quote contradiction to Merman-Wagner, because it assumed locality. And indeed, the actual proofs of these theorems depends on locality. Goldstone theorem that you get gapless modes from continuous symmetry breaking, that depends on locality. When we talk about universality classes of phase transitions, when we say this transitions in the Heisenberg universality class, this transitions in Hertz-Millis universality class, whatever, each of these sorts of classifications of what type of phase transition it is, it relies on locality, or the traditional understanding is that the universality class only depends on symmetry and dimensionality.